Hi there, my name is Franky de Bruyne. Welcome to this channel on signals, systems and control. Today we'll talk about the complex valued Fourier series. This video follows on a video on the real valued Fourier series. You'll find the link to this video in the description. This is a brief summary of what we've covered in the previous video. So f of t here is a real valued function. It's periodic of period t, and associated you have of course the fundamental frequency omega 0 2 pi over t. What you see over here is the so-called exponential Fourier series, and we have seen in the previous video that there are at least 3 other interpretations, but basically this formula says that you decompose f of t in a sum of sines and cosines at the harmonics of the fundamental frequency. C of k is called the Fourier coefficient, and it's computed as follows. So basically it's the average over a period of the function f of t of the function itself times a complex exponential. So this is a rotating vector over here at the harmonic frequency k omega 0. So if k is positive, this rotating vector will be turning clockwise, and if k is negative, it will be turning counterclockwise. As you can see from the formula, and if f of t is real valued, right, then if you take the conjugate of c of k is a complex number, right? So if you take its conjugate, since this is a real value, the only thing that will change here is the minus that will become a plus, right? And then you see that ck conjugate is exactly c minus k, and we have seen in the previous video that this leads to a amplitude line spectrum that is even and a phase line spectrum that is uneven. This is interpretation 4 of the Fourier series that I've shown in the previous video here for a square wave. Notice that there are only uneven harmonics. We have only considered 7 terms in the approximation. Basically, all phases rotating clockwise and all phases rotating counterclockwise have been grouped together, and this is what you see in the animation. If you take then the vector sum, you obtain the function f of t. It's also the real part, and this is what you see on the screen below in green. Of course, and this is important here, the imaginary part here is always 0, as you can see in the red curve. This is by construction because c of k obeys this property. ck conjugate is equal to c minus k. Let us have a look at this in more detail. So here we have our exponential Fourier series of the function f of t. If we look at harmonic k, and we'll assume here that k is positive, well, in this sum we'll have 2 terms, one corresponding to a positive index k, right, and one corresponding to a negative index k. This will be related to a phasor turning counterclockwise at the harmonic k times omega 0, and this phasor here will be turning clockwise. If we remember that c minus k is really ck conjugate, and if you write ck in its polar form, right, here you have the modulus and here the argument, of course, then you have that ck conjugate is similar but with a minus sign over here. So what you can do now is inject all this in this expression over here. This is what you obtain over here. So what I've used here is the property of the exponential, that the exponential of a plus b is the exponential of a times the exponential of b. So here it is rewritten in such a way that we can now use Euler's identity. And this is what we obtain. As you can see, the imaginary part of course is 0, and this is of course closely related to the second interpretation of the Fourier series that we've introduced in the previous video. For those who like to see things visually, we can represent this in the complex plane, right? So here we have the imaginary axis and here the real axis, right? Imaginary axis. So let us have a look at both terms, right? We'll draw this one first. Imagine that at a certain time it's at this position over here, right? Of course, the length is the modulus of ck, and the angle here is the argument of ck, right? This one will be turning counterclockwise, so we'll name it ck exponential of jk omega 0 t, right? So now we can have a look at this one over here, right? And because of this property, we see that it is the complex conjugate of this one, right? So this means that this one will be on the other side of the real axis. It's mirrored with respect to the real axis, right? So this one will be turning clockwise, right? And this is c minus k exponential of minus jk omega 0 t, right? And this one is of course ck conjugate, right? And these two terms, what you can now do is take the vector sum, right? So if you take this one and you come and put it over here, you take the vector sum, and what you obtain is indeed, well, something that has no imaginary part, and this is what we see over here. What we'll do in the next animation is to group all harmonics together with the positive index and the negative index, and what we'll see is this phenomenon happening for each harmonic and the fundamental frequency. So for k is equal to 1, 2, 3 and so on. Well, let us have a look at this new animation and this new interpretation. First, as you can see in the line spectrum, you can see the property ck conjugate is c minus k, because you can see that the amplitude spectrum and the magnitude of ck is an even function of k, whereas the argument of ck is an uneven function of k. Again, we'll take the approximation of the square signal using 7 terms only, and as you can see in the line spectrum, only the fundamental together with the odd harmonics are present, so the harmonics 3, 5 and 7. For each harmonic and for the fundamental, of course, you will see a vector rotating counterclockwise, that's the one in red, and then you'll have the conjugate, right, the one that is turning clockwise, and that is the one shown in blue. And as you can see, at all times, if you add, if you take the vector sum of those two, well, you obtain something with a zero imaginary part. Well, without spoiling things too much, if you take the Fourier series of complex valued functions, you will no longer have this property ck conjugate is equal to c minus k. We will see in future animations that the red rotation vector corresponding to positive indices and the blue rotation vector corresponding to negative indices will add up to produce, of course, the real part of the complex valued function, but also to construct its imaginary part. Well, let us now have a look at the complex valued exponential Fourier series. So f of t can now be complex valued. This means that f of t can be decomposed in its real part and its imaginary part. Of course, the obvious thing to do is to take the Fourier series of the real part of f of t and of its imaginary part. Since both functions are real valued, what we can do is use the theory that we have just reviewed and compute the Fourier series of the real part of f of t and the Fourier series of the imaginary part of f of t. And associated, of course, you have two sets of Fourier coefficients, one set associated to the real part of f of t and one set associated to the imaginary part of f of t. So all the Fourier coefficients, the ones associated to the real part and the ones associated to the imaginary part, are complex numbers. Of course, we are interested in f of t, so what we'll do is take the real part and add j times the imaginary part. So this is what is written over here, and using distributivity you can rewrite it as follows. So what we'll do over here is call this complex number here C of k, and what we recover is the formula that we had also obtained for the real valued exponential Fourier series. Well, let us write the C of k that we find in this formula. As you can see, it's this expression over here. What we can do is plug in those expressions over here and use distributivity, right? And then you obtain this expression. This is the real part of f of t plus j times the imaginary part of f of t. So here we obtain our complex valued function f of t, and again we recover the formula that we had obtained for real valued exponential Fourier series. So here's the summary. We work with complex valued and periodic functions of period t. This means that the functions f of t in the complex plane will produce a closed curve as the function is periodic. The fundamental frequency, as before, is omega 0, which is 2 pi over t. Well, then we obtain the two formula that we had obtained also for real valued functions, right? So the decomposition is exactly the same, and the way we compute the Fourier coefficients is exactly the same. The only difference in here is that, of course, f of t is now a complex valued function. So this means that if you take the conjugate of c of k, well, you have a change of sign over here, but you have to replace f of t by f of t conjugate, and this means that the conjugate of ck is no longer c minus k. So this property that we had for real valued functions is no longer valid. Well, let us have an example of a complex valued function, and this function is here the rabbit function that you see here shown in the complex plane. Here on the left you see the x and y coordinates of the rabbit function. So this is really the real part and the imaginary part that we've spoken about before, and you see them represented as a function of time. As in the previous video, we have considered a period of 1 second and a period that is centered around t is equal to 0, so from minus t over 2 to t over 2. Here on the right you can see the light spectrum. As we have lost the property that ck conjugate is equal to c minus k, we have lost this symmetry around the y-axis over here. You can see that the magnitude spectrum is no longer even, and of course the argument or the phase spectrum is no longer uneven. So let us have a look at a certain index k. Associated to that will be a phasor, and its length will be the modulus of ck, and this phasor will turn from minus k pi plus argument of ck, and it will go up to k pi plus argument of ck. This is something that we have seen in the previous video, and it's valid for periods that are centered around t is equal to 0, as is the case over here, right? So this means here that this phasor will make k full turns, right? And depending on the sign, it will be either counterclockwise or clockwise. So if k is positive, it will be counterclockwise rotation, and if k is negative, it will be clockwise direction. So the argument of ck is just a phase shift. It will affect the starting position of your rotating vector. As you can see, in this case here, I've considered indices from minus 10 to 10, so I have 21 Fourier coefficients. Well, let's have a look at the computation of the Fourier coefficients, and this allows me to show the nice pictures that we have generated. And we'll stop here because we see our rabbit over here. So this is the computation of C0, and what we have to do to compute ck is multiply f of t by the exponential of minus jk omega 0 t. Here k is 0, so this is really what you see here is the complex function f of t, the rabbit function, right? So previously, since f of t was, well, real valued, what you had here is f of t times the cosine k omega 0 t, and here you had the f of t times the sine k omega 0 t. Since f of t is now complex, right, this is no longer true. So what you see here is the real part of f of t exponential of minus jk omega 0 t, and here the imaginary part of the same function, right? And then what you have to do here on the right is take the average of the real part of this function over time, over one period, right? You take the average and you do the same for the imaginary part, right? Since k is equal to 0, what we obtain here is a C0, where you have the real part over here and the imaginary part over here, and this corresponds to a complex number that is located at the center, if you can say this, at the center of the rabbit. Well, here you have the computation of C1. Now it's f of t times the exponential of minus j omega 0 t. This is why you have, well, the original function distorted. You take the real part, the imaginary part, you plot it with respect to time, one period, and then you take the average of the real part and the average of the imaginary part. So here you have the real part of C1 and the imaginary part of C1, and as previously, well, instead of writing C1 in Cartesian form, you can also write it in a polar form, and this is really what you read in the line spectrum. What I've done for C0, C1, you can do for the other Fourier coefficients. So what you see over here is the animation, right? It's the approximation of the rabbit that you see here in blue using the Fourier series approximation, using here 21 Fourier coefficients. So here we have the fixed vector that corresponds to C0, right? And then here you have in red and in blue the first harmonics, right? They are turning once per period, and this is the index that corresponds to k is equal to 1. It's turning counterclockwise, and here this is, well, the rotating vector associated to k is equal to -1, and as you can see, it's turning clockwise. And then you can have a look at, well, the second harmonic, right? And then this one over here is the rotating vector associated to k is equal to 2. It's turning counterclockwise, right? And here you have the rotating vector associated to k is equal to -2, and this one is rotating clockwise, right? And you can continue to do this for the other indices. As we have taken only 21 Fourier coefficients, well, you can see that the approximation is not that good. So what I'll do is stop the animation over here, and we'll make a comparison of these approximations with several examples using different numbers of Fourier coefficients. Well, if you look at the complex number that is produced and you take its real part, well, what you have is the x-coordinate of our rabbit, and this is what you can see below here in green. And if you take the imaginary part, you obtain the y-coordinate of our rabbit, and this is what you can see here on the right in red. In this animation, we compare the approximation of the rabbit by the complex Fourier series for a number of Fourier coefficients, that is respectively 21, 41 and 101. And of course, as expected, when the number of Fourier coefficients increases, well, the approximation of course improves. This concludes this video on the complex Fourier series. I hope you liked it, and if you did, don't hesitate to like the video and to subscribe to the channel. See you soon.